Last time we looked at the arc length formula, and the arc length formula is really nice because all it is the integral on the interval of speed. Speed is the magnitude of the velocity vector. And so we did a couple of examples, and that was fun. And now we're going to look at an idea called the arc length function. So let me set up the arc length function. Remember we talked about when we did parametric equations for a line that the parameterizations are not unique, that you can come up with a different parameterization that's just as legit. It's just that, you know, it may, it could use a different parameter and what have you. So other parameterizations are still true and they're valid. And it turns out that all curves, not just parametric equations for lines, can be parameterized non-uniquely and still be valid, still show the same curve or whatever. So how do you get different parameterizations? Because you can't. So one way, and this is classic, is to use the arc length function. This is classic, to sort of reparameterize a vector valued function, which could include a line. I mean, vector valued functions could be you know, curves, where curves could be graphs of straight lines. And it seems silly, but okay. So take a look at this little double example here. This curve here with components t squared and t cubed, which is called the twisted cubic, is a nice parameterization of that curve, okay? And the same curve can be parameterized with components e to the u, e to the 2u, and e to the 3u, where u goes on this interval instead. So these are equivalent. These are equal. The curves match, everything matches. Well, they look totally different. I understand. But they're two different parameterizations of the very same curve. And you want to care about this because later on in this course, we are going to parameterize functions. And you have to know how to do that on your own. And I showed you some of the easy ways to parameterize on your own in a previous lecture. So how could you come up with just a brand new parameterization out of the blue? Because you can come up with infinity different parameterizations for the same curve. But this particular approach we're going to use uses this arc length function. So let's talk about the arc length function first, and then we'll show how to use it to reparameterize a curve. Fine. So say you've got a curve with components f of t, g of t, h of t, as long as t is greater than some number a, fine. The arc length function s, and remember s is the classic letter that we use for arc length, s, and the lower limit is a, and this t is variable. The a is a fixed number, and I want to say that traditionally the a is equal to 0, although it doesn't have to be. Wow. I've got a ghost in my machine that's doing something weird. Strange. Okay, so this is typically a is equal to 0, but it doesn't have to be, okay? Now, because the upper limit is a variable, t, and I know a lot of you are not used to that. You're like, oh, I thought the limits on an integral always have to be pure numbers all the time. Not necessarily. When you were in Calc 1, believe it or not, you may have seen that upper limit be equal to a t when you did the fundamental theorem of calculus. So this is a variable. So you're not allowed to have oh, see, there it is again. It just disappeared. All right, I got to stop. So we're going to come up with a brand new parameterization. And folks, this is done a lot because like my master's thesis many years ago was about parameterizing curves in a very interesting way. Yeah. If you're into computer science, you might be interested in learning about it. Anyway, so the arc length function is this integral that looks like the arc length. It's like, well, what's different? Doesn't this look like, you know, the integral of speed? It's almost the same, where this upper limit is variable, and because it's a t, we're kind of using up a t now. You're not allowed to use the same letter variable in a limit that you are in the actual integrand. And we're going to do this more and more with that rule when we get into double and triple integrals. So it's good to see it now. That's why you see all these u's and du, because you have to have a different variable of integration that doesn't match the variable that's in one of your limits. Okay, fine. And if I write this a little more compactly, the integral from a to t of the magnitude of the velocity vector, it's just the same. Okay, fine. Now, this looks like really complicated. So what are two cool facts about the arc length parameter or the arc length function? If you use this arc length function to reparameterize your vector valued function, okay, so there's your arc length function, then some things kind of fall out of it. The derivative of this arc length function is going to be the speed itself, evaluated at t, which is the same as, if you want to use different notation for the velocity vector, you want to use v instead of r prime. They're both the same. And here's something even more cool. Suppose, and this is a very special case, your speed is a constant, and it happens to be 1. Well, then it makes this integral super easy to integrate, because then you're really just integrating 1 with respect to u. And so that would just be u, where u is going to be evaluated between the limits on that integral. And then when you substitute in the upper limit and then substitute the lower limit, and so on. Now, if a is equal to 0, which is very common, then you would have u evaluated between 0 and t, which would just give you t. So you may be thinking like, okay, so what? So in English, here's what number 2 is saying. If it turns out that speed is equal to 1, you may conclude, in fact, you're guaranteed that the following is a fact. The parameterization is done using the arc length function. So the curve is parameterized using the arc length function. That's a guarantee. You get that for free if your speed is a 1. Okay, let's just do an example or two of this arc length function stuff, and then we'll talk about curvature. Okay, so take a look at this curve. And this is another one of those helix guys. In fact, I think we worked on this one a few times and found some like the unit tangent vector and the unit normal vector. But now let's do the arc length function for this curve. So S would be equal to, and I'm going to have A be equal to 0 just because it's common. So 0 to t. You're not always guaranteed that, just be careful. And we're going to take the integral of speed, r prime of u du. Now, if you recall from a previous time of working with this, it turned out that speed, r prime of t, I think was equal to 2 square root of 10, because we worked on this with a previous example. So what we're doing here is we're going to have this 2 square root of 10 as our speed. And then and that's just a constant. Oh, we're lucky here. And then the integral of 2 square root of 10 with respect to, oh, I should use u, sorry, this should be u, is just 2 square root of 10, u, where u gets evaluated between 0 and t, but that's just 2 square root of 10 times t. Fine, so that's an arc length function. So what you can even write is your arc length is a function of time t, and you can write it like this as your final answer for part A. There's your arc length function. S of t is 2 square root of 10 times t. Fine. So what? We're going to use this arc length function to reparameterize this vector valued curve. So how do we do that? Very carefully. So let me rewrite my answer to letter A, where I just write it as S is equal to 2 square root of 10 t. And then what I'm going to do is I'm going to solve this little formula for t, which is pretty easy because we'll just divide both sides by 2 square root of 10. So what do we have now? T is S is arc length, all over 2 square root of 10. And then you'll substitute this into R of t. In other words, look at your R of t vector value function up here. Everywhere you see the letter t, and I see it happening 3 times, you want to substitute S over 2 square root of 10. So your new parameterization, which we're going to call R of S, is going to look like, leave a lot of room here, 2t, but that's going to be S over 2 square root of 10, comma, 3 sine 2t, but that's 2 times S over 2 square root of 10, comma, 3 cos 2 S over 2 square root of 10. Of course, you want to reduce and make this look a little prettier. So I'm going to reduce some of these to lowest terms. These 2's cancel, these 2's cancel, these 2's cancel. So it looks a little nicer when you have S over square root of 10, comma, 3 sine S over square root of 10, comma, 3 cos S over square root of 10. And I'm done. This is the new parameterization for the vector value curve. It's common to do that. And the curve will look the same if you graphed it, although the intervals may be different for different portions of the curve. Now, what we were told in the previous theorem up here is a guarantee that if your curve is parameterized using the arc length function, then the speed will be 1. So it says, hint, first use your answer from part B to obtain R prime of S. Okay, we have R of S right here. There it is. Yay. So what is R prime of S equal to? Okay, well, we'll just take a derivative of each component. All right, the derivative of the first component is just 1 over square root of 10. And then when we differentiate a sine function, we're going to get a cos, and then we're going to use the chain rule. So we have 3 over square root of 10 cos of S over square root of 10. And then finally, differentiating a cos is going to give me a negative sine, chain rule, negative 3 over square root of 10, sine S over square root of 10. Fine. So there's the derivative. So now go get speed. That's the magnitude. So you're going to have the square root of the sum of the squares of all of these components. It's going to be kind of messy. I know. And sometimes, you know, Calc 3 gets a little messy. And as before, you'll notice after squaring that the last 2 terms have a common factor of 9/10, because when you square 3 over square root of 10, you get 9/10. So when you factor out that 9/10, you're going to have a cos squared plus a sine squared factor, but that goes to 1. So after simplifying, this is going to look like 1/10 plus 9/10. But wait a minute, that's 10/10, and square root of 10/10 is square root of 1, which is 1. Boom, we're done. So when you get that happening, what that means, even if the letter were different, let's say those S's were Q's or something like that instead of an S, the fact that speed was a 1 tells me that that parameterization was parameterized using the arc length function. So that's kind of cool that you get that guarantee. Now for some weirdness with this arc length, that's kind of fun. Once you parameterize your curve using arc length, you can travel a distance of S along a curve and then figure out some things from there. So where on the curve, and this is the original curve, are we after traveling a distance of pi square root of 10 over 3. Now this is an S, this is an arc length. You know, so you know, here's your helix, you know, and they're saying that, assuming that we're starting here from t equals 0, would that start at the origin? No, that actually, t equals 0 looks like it would start at what, 0, 0, 3? Like right here. So you traveled some distance here, and that's an arc length. So this distance would be, you know, a weird number, pi squared of 10 over 3. So what position are you when you finish? So where's this finishing position? Where is this? So the way you do this problem is arc length, and we're going to use the arc length function. Remember, it was 2 square root of 10t, but they're telling you what the arc length is. So you substitute pi square root of 10 over 3 for arc length, and then solve for t, and this is just an algebra problem now. So I'll divide both sides by 2 square root of 10. And once I do that, it looks like the square root of 10s are going to cancel, which is nice. Woo! Then what? I get t is equal to pi 6, and then substitute this into r of t to get your position of where you are when you're done traveling that distance. So it turns out that r of pi 6, what do you have here? 2, you have your first component, 2t, that's 2 times pi 6. Then you get 3 sine of 2 times pi 6, which that looks like sine of pi thirds. And then you get 3 cos of 2 times pi 6. So that's cos of pi thirds. So your final answer here is you're located at position pi thirds. And then I think you're going to get 3 square root of 3 halves for the second component. And then you get 3 times a half, which is 3 halves for the last component. And that's where you're located when you're done traveling that distance, if you started at t equals 0. So that's kind of fun. And then finally, a nice true or false question. This curve, big R of t, t squared, 3t squared, is it parameterized by arc length? Yes or no? Like, how could you tell? I don't know. You can't guess, okay? But remember our guarantee from the theorem. The guarantee is if the speed equals 1, voila. That means it's parameterized using the arc length parameter. If the speed isn't 1, it ain't the arc length parameter. So in order for us to distinguish between true or false here, we're going to ask ourselves this question. Is the magnitude of the velocity vector equal to 1? Well, first let's go get this velocity vector. You know, r prime, that's pretty easy to get. I get 1, 2t, 6t. And if I get the magnitude of this velocity vector, you know, take the square root of the sum of the squares. Does this look like it's going to be even a constant, folks? Does that even look like it's going to be square root of 1 to you? I don't think so. That's going to be some function of t, which is pretty typical for speed. So it's definitely not a constant, and it's definitely not going to be a 1. So the answer is false. This lovely curve is not parameterized by the arc length parameter. Oh, well, still a nice vector valued function. Though. You could still do fun stuff with it. So we're done talking about arc length and the arc length function. Congratulations. Now we're going to do curvature. Okay. Here we go. Curvature. All right. So this is kind of fun because you can measure how curvy a curve is. You know, like how curly is your curve at a certain point? You can actually measure it. Do you have like a curly measurement tool? Well, sort of. And we're going to look at the definition of curvature. So it gives you a measurement of how curly something is. So how sharp does a curve bend? That tells you how curvy it is. So take a look at this diagram right here, and it, you know, at different points, it varies in its curvature. Like over here at point P, it's a little bit more curvy than it is at point Q. Can you kind of tell why? Just by looking at it? There's more bend to the curve there at P than there is at Q. So we can look at it with our eyeballs and go, yeah, it looks more curvy, but how do you measure it? Like, you know, like, is it a 2 or in curviness, or is it 7, or is it a 0.2? What is it? So the way the mathematicians decided that, hey, since it's obvious that the more bend that a curve has, more bendy, I don't think that's a word, but I just made it up. The curve is that has more curvature. So what's going on when it has more curve? And it turns out that if you look at the unit tangent vector, remember big T from last lecture, and you examine it, it's changing direction a lot more rapidly than it is around points that aren't that curvy. Like over here at Q, like let's look at right before Q. Here's a tangent vector. Here's another tangent vector at Q. Here's a little bit later. Those kind of are flattening out, and those unit tangent vectors are kind of pointing sort of in the same direction. It doesn't look like they're changing direction much. So the way we calculate curvature is we calculate the magnitude of the rate of change of the unit tangent vector with respect to the arc length. So the official definition, and they use K to denote arc length. Why K? Why not something? I didn't make this up. This is all textbook. You take the magnitude of the derivative of big T, but if it's been parameterized using the arc length parameter. So it's very specific. You could also write this as magnitude using different notation, dTds, same thing. Where your unit tangent vector, remember from last time, is defined as the unitized velocity vector. Now, because you're not always guaranteed that your vector valued function is parameterized using S, the arc length parameter, I rarely use this definition. In fact, I have a full confession. I never use it. I'm just going to put rarely used. And I'm totally okay if you never use it either, because it's kind of a very special case to have a vector valued function parameterized using S, the arc length parameter. So what's another curvature formula? There's a couple other ones that you can use. Yeah, they're all, in fact, we got 3 more. Oh my goodness, we got all these choices. Well, which one's the best? I'll just tell you, it depends on which problem you're doing for which one's going to be the easiest to use. It depends. My personal favorite is this one right here. I just like taking the magnitude of big T prime and dividing it by speed, the magnitude of R prime. That's my personal favorite. The only time I don't use that one is if big T prime is turning out to be a real pain in the behind to get, which sometimes it is. Like if you end up to get big T prime, you have to use the quotient rule with the chain rule, and it's like a big hot mess. Sometimes that happens. It's like, oh, this is going to take me like forever. Then you may want to use this one instead. So this one involves taking a cross product of the velocity and acceleration vectors, and then take their magnitude and then divide it by speed cubed. Yeah. And we'll do both of those in a moment. And then the last kind of curvature is very specific, because this only works in 2D. And a very special case of 2D, where you have the curve already handed to you and written as y equals some function of x. Okay? You don't always get that. But if you do, then you can use this curvature formula. All right, so let's do some curvature stuff. So prove that lines have 0 curvature. Well, do they? I mean, come on, look at a straight line. Does that thing look curvy to you? I don't think so. So I would hope that if this curvature formula is worth its salt, it should have every line out there have its curvature measurement be 0 because there's no curve to a straight line. Fine. So here's a vector valued function with the parametric equations there as components, and that would graph a straight line. So show me that the curvature will be 0. And I'm going to use this formula right here. The magnitude of big T prime divided by speed. So that's how I'm going to roll. So first I got to go get R prime. And that's pretty easy because in this case, it's going to be a constant vector. That doesn't always happen, but it's nice. So then my big T, which is defined as the unitized velocity vector from last time, is just going to be the vector -1, 2, 7 divided by square root of 1 squared plus 2 squared plus 7 squared. Uh-oh. What the heck is that? Well, oops, I don't want to do that. Okay, 1 plus 4 plus 49. I think that's square root of 54. And since 54 is equal to 9 times 6, this square root of 54 you can write as 3 square root of 6. So your big T, when I rewrite it nicely, where I distribute my scalar, is going to look like this. -1 divided by 3 square root of 6. 2 divided by 3 square root of 6, and 7 divided by. It's a constant vector. Doesn't always happen for big T, but it's nice. So now go get big T prime. Yeah. Well, the derivative of a constant is 0. So it looks like big T prime is the 0 vector. So now when you go, okay, curvature K is going to be the magnitude of big T prime divided by speed. And we already know what speed is. That was the square root of 54. I'll just rewrite it as 3 squared of 6. But this is just going to be the square root of the sum of the squares of a bunch of zeros. And your final answer is 0. And that's what we needed to prove. So, and that works for any line. Just because of the nature of lines. Yeah. Nice. Okay. Now something kind of cool, especially if you're going to be a civil engineer. Quick survey. How many civil engineering majors do we have in the room? I'm going to stop here. Show of hands. Put up your hand. Any civil engineers? Civil engineers in the room. 0? Oh my goodness. Okay. Nobody? Okay. All right. Let's try something else. How many computer science majors in the room? Put your hand up. 1, 2, 3, 4. I think I saw 4, yeah. That's it? Okay. 5. Wonderful. Wonderful. Okay, put your hands down. One more thing. I want to check to see how many electrical engineers we have in the room. Any electrical engineers? 1, 2. Okay. How about a mechanical? Any mechanical folks? All right, there's 1. Okay. All right, we get a few folks. All right, but no, wow, that's weird. No civil. All right, fine. Interesting. Okay, so I just thought this would be interesting for some civil engineers when you're talking about building like freeways and freeway on-ramps. Let's take a look at circles. I'm going to just draw a couple of circles here. Here's a circle, and then here's a circle. 2 circles, small one, big one. What do you think? Do you think circles all have the same curvature, or do you think that one of these circles has more curve than the other one? If that's the case, which one has more curve, the small one or the big one?
The small one.
That turns out the small one is more curvy. It's going to have a higher curvature. And why is that? Well, think of yourself as driving in a car. If you're driving around a tight circle, you have to really crank that steering wheel over versus if you're driving in a very large road that's, you know, part of a big circle, one of those rotaries or something. Yeah, you know, you have to crank your steering wheel over a little bit, but not real hard. So it's not as curvy. So what are we saying? That it's dependent on your radius. The larger your radius is, the less curve you have. So it's an inverse relationship. It's an inverse relationship. In fact, curvature will actually equal 1 divided by the radius of your circle. So as you can imagine, when the denominator is smaller, the overall fraction gets larger. So let's prove that K is 1 over R for a generic circle. And if you don't believe this is a generic circle, let R equal 2 and use your graphing calculator in parametric mode and graph it, and you'll get a circle of radius 2. If you put R equals 5 in there, you'll get a circle of radius 5. Fine. So we're going to go get R prime. And that'll give us negative R sine, R cos. Then we're going to get speed. So that's going to be square root of the sum of the squares of our velocity vector. And then, of course, you know, you've seen this happen before. R squared is a common factor. And so when you factor it out, this sine squared plus cos squared is 1, you get square root of R squared, and we'll just get R. Actually, the absolute value of R, because you want your curvature to be something non-negative. Now it's time to get big T. That means unitize your velocity vector. Yeah. You know. So what's going to happen is the R's will cancel. Ooh, that's nice. So then big T isn't that bad. Then what? Take big T prime. And I get negative cos, negative sine. And now you're ready for the curvature formula. Curvature, big K, is equal to the magnitude of big T prime divided by magnitude of R prime, speed. So you're going to get the square root of big T prime. So you're going to basically get cos squared plus sine squared underneath that radical divided by R. And this is really the square root of 1 over R, but that just simplifies to 1 over R. And there you go. All circles will have a constant curvature of 1 over R. Nice. Good to know, especially if you're building a highway. So the moral of the story, in case you missed it, is circles with small radii have larger curvature. Circles with smaller radii larger curvature. While we're on the subject of computers, and you guys solved my problem so nicely, so thank you. What do you do when your Surface Pro is running out of memory? I thought I bought a hard drive that was big enough. I know, get an external hard drive. I don't want to, but I might have to. I don't like that. Okay, example 9. So this one's nice. It's classic. You're probably going to see it in your MyLab math, I think. I think I put something like that in there. So just follow what's going on here, and you'll be fine. Show that the curvature of a helix is constant. It's going to turn out to be a constant. Is it going to be 1 over R? Well, there's no R involved here. I mean, if I graph this helix where you've got A and B positive, it's going to look like that, you know, that slinky like that. So the curvature kind of depends on where you are, but not, you'll see it will be a constant. It's going to depend on something. Okay. Go get R prime. It's going to follow the typical strategy here. So when I take the derivative of this vector valued function, I get negative A sine t, A cos t, and the derivative of dt is b. Fine. Go get the speed. All right, that's the magnitude of velocity. I got the square root of the sum of the squares of the components. I'm just going to write them as squared already. And then, of course, you know, when you factor out the common factor of a squared for the first 2 terms, you get the other factor is the trig identity. That didn't look too good. That's a sine squared of t plus cos squared of t. This is just 1. So this is just going to end up being the square root of a squared plus b squared. Cool. Now you're ready to put it together because your unit tangent vector, which is just the unitized velocity vector, will look like this. Fine. Now what? Go get big T prime. Okay, the derivative of negative a sine t all over this constant square root of a squared. The constant just stays itself. You just worry about taking the derivative with respect to t. So the derivative of sine is cos. So that first, and the negative will stay there because it's not changing in sign. But then when you take the derivative of the second component, where you're taking the derivative of cos, you'll get a negative sine. So you'll get negative a sine t over that square root. And then the last component is a pure number, constant. So its derivative is 0. That's convenient. Nice. And we're almost done because the curvature formula is magnitude of big T prime divided by speed. So you're going to go the square root of, and so you're going to have all of these components squared. The 0 squared, of course, is just 0. Who cares? And then we did get our speed. It was that square root. So clean this mess up. And when you do, the common factor for those terms under the radical would be a squared over a squared plus b squared. And then you'll have that trig identity because cos squared plus sine squared is 1. And then when I use the law of radicals, that's an a squared. I'm trying to write too fast here. You'll end up with a over a squared plus b squared. And that is your curvature for this helix. It's going to be a constant. It's not dependent on where you are. Some curves do rely on where you are, like parabolas. They're curvier closer to the vertex. And the further away you get from the vertex, your curvature is not that curvy. So it is dependent on the parameter. This helix, no. Circles, no. So speaking of curvature of a parabola, we're going to do one next. And then we'll finish out with doing something called an osculating circle, which is kind of what civil engineers would like to do. So you can use your curvature formula like we did before, the big T prime magnitude divided by magnitude of r prime. It works. But here's the problem. For this particular example, big T prime, I don't want to get into it. I'll just tell you right now, it will be a disaster because you're going to have quotient rule and within the chain rule, and it's a lot of radicals floating around, and it gets pretty ugly. You can do it, but it gets ugly. So a better way to circumvent that is to use the cross product version of your curvature. So you don't have to run into all this really messy derivatives. Fine. How would you know that? Well, you wouldn't unless you've done some of this before. But I'm just telling you right now, once you try to find big T prime, it's hard. So big T prime is a disaster. Lots of derivative rules going on there and algebra, because you end up with complex fractions with radicals in there. And I used to do this in lecture or something like it, but it's kind of hard to test because it's takes so much time. So don't worry, I'm not going to make you do it. So it's a disaster. And so basically what I mean is it's too much of a challenge. So let's not. So let's use this version of curvature. We'll take the magnitude of the cross product of velocity and acceleration, and we'll divide by speed cubed. A little easier. Still have some work, but it's a little easier. So let's go get the velocity vector. Oh, that's easy. And this is just a 2D vector, a valued function, so it's not too much. So you're going to go, oh, no, it isn't. It's ijk. Sorry. My bad. There is 3D. Okay. The J is silent. 0. So r prime is going to be what? 2t. There's no j, so 0 for that. And then derivative of t is 1. Oh, that was easy. R double prime, that's acceleration. We're going to get a constant vector, 2, 0, 0. Does that always happen? No, but it's nice because now when we take a cross product, having a few of those be zeroed out is kind of sweet. So we have I hat, j hat, k hat in the top row. We have 2t, 0, 1 in row 2, and the last row is 2, 0, 0. All right, here we go. I'm just going to do this on the fly. It's going to turn out that the first component is 0. So you'll have 0 I hat minus 0 minus 2 j hat plus 0 k hat. So you're going to get this constant vector 0, 2, 0 for the cross product. Fine. What is the magnitude of that? Well, should be kind of obvious, but we'll do it in slow motion anyway. And I get square root of 4, which is 2. And now what is the speed? Speed is the square root of the sum of the squares of velocity. And that is not a constant. Okay. And then we're almost done because your K is going to be this cross product magnitude divided by your speed getting cubed. And if you want, you can leave it like that, or you can, I would do it maybe like this, write it with a rational exponent, 2 to 3 halves. Now, the last part of this problem, kind of missed it here. After you get your curvature, which we did, and it's going to be a function of time. It's not going to be constant. It's going to depend on where you are on your parabola. Where is the parabola curvature maximized? Well, you could do, you know, take to the derivative, set it equal to 0. Well, I don't know. So what's a quicker way of doing it? When do you think that, when is this going to be maximized? It's a little bit tricky. It's going to turn out, and like I say, you could do your calc 1 on it. Use the chain rule, take the derivative, set it equal to 0, solve for t. It turns out it's maximized when t is equal to 0. So on the curve, it'll be, when you plug t equals 0 into this vector value function, you get the point 0, 0, 0. Which I believe happens to be the vertex. Yay! And so what is that maximum curvature? Well, when you plug t equals 0 into this curvature formula, you're going to get 2 over 1 to the 3 halves, which is just 2. Okay? And that's it for that example. So that's example 10. And the big point on that one was it was a little easier to use a different curvature formula. Okay. Last but not least, and this is a problem I took directly out of MyLab Math because I had so many students ask me about it. They kept getting stuck, and it's a tricky. So I'm going to walk you through it nice and slow so that when you do it on MyLab Math, you'll be fine. Okay? But it's kind of cool because it involves some algebra, lines, and the distance formula. So it's jam-packed with material. I mean, it's a true engineering, it's an engineer's dream type of problem where you have to like use all your elements to solve the puzzle. So that's the kind of fun part of it. Although some people may not like that. I don't want to use all that many brain cells to solve a problem. Okay. So here's the idea. There's this thing called an osculating circle. So what the heck is it? I just like to show you what it would look like. If you have some curve somewhere, that's not it. Let's get a new page. Say a curve is curving around. So I'll just do it in 2D for fun. Let's say you had some curve. Let's just do a parabola. What the heck? Here's a parabola. Okay. So let's say right here is the most curvy part of the parabola. Yeah, that's true. Right there at that moment, what if you snuggle up? I call these osculating circles snuggling circles, not a technical term. But what is the radius of the circle that can snuggle up right inside that parabola right there at that point? That's called the osculating circle. Kind of snuggles in there. So remember that K is inversely related to the radius of the circle. So when you get one of these osculating circles, the radius of the circle, whatever it is, you can find it because it's going to be 1 over the curvature if you get the curvature first. And so then you can figure out the snuggling radius there. That's an osculating circle. Kind of cute. So we're going to do a little osculating circle issue here. So here's a parabola, and they give you y equals ln of x. Now you're like, well, y equals ln of x doesn't really look like a parabola. Well, yeah, it's kind of like, you know, sideways parabola if you graph it. Has that parabolic look to it, doesn't it? It's not your usual parabola, but it's got sort of a parabolic arc to it. Fine. First, we're going to go get the curvature. Now we're going to use that last curvature formula. Remember, there's 4 of them total. We've already used 2 out of the 4. I haven't used the one with S yet. I'll let you worry about that one. But the one where if you're given y as a function of x, you can use this as your curvature formula instead. You could just go right to that. So absolute value of y double prime divided by the quantity 1 plus y prime squared to the 3 halves. Weird, I know. So we're going to use it because we want to do something different. Or you could parameterize this curve and then do one of the other parameterization curvature formulas. So we're going to use K equals absolute value of y double prime all over the quantity 1 plus y prime squared to the 3 halves. Woo, yikes. All right. So what do we got? Well, we have y equals ln of x. Okay. Well, we're going to need y prime and y double prime to substitute into this formula. Okay. So y prime, the derivative of ln of x is 1 over x, which you can also write as x to the negative 1, which I like to do before I take the next derivative. So y double prime is negative 1 x to the negative 2 using the power rule, which I'll rewrite with positive exponents, negative 1 divided by x squared. Okay. We're getting somewhere. So what is your curvature? You're going to take the absolute value of y double prime, and you're going to divide that by the quantity 1 plus y prime squared to the 3 halves. So this is kind of a mess, but you know, it works. So what would they want us to find some information at the point when x is 1. So let's evaluate the curvature k, which is a function of x, when x is equal to 1. Well, we're just going to substitute x equals 1 into this big messy formula. Absolute value of negative 1 is 1. 1 plus 1 is 2. So I get the curvature is this weird number when x is equal to 1. Now on your graph, folks, when x is 1, on your ln graph, it's right there. The point is at the point 1, 0. It's right there. You can kind of almost think of it as being the vertex of this sort of parabola here. So here's the plan. This is where it gets a little weird now. I want to snuggle up an osculating circle right in there. Okay, there he is. He's so cute. So what would the radius R be for this osculating, snuggling circle? Well, remember the radius is going to be 1 over K. So this is going to be 1 over 2 to the 3/2. And then if we turn division of fractions into a multiply problem, this is going to be 2 to the 3/2, which is the same as 2 square root of 2. Okay, fine. So what are we saying? We're saying that the radius of this circle that can snuggle up right inside that curve, it's 2 square root of 2. We know that to be true. Okay. Now they want us to sketch the circle. I did a job of, I just sketched it. I'm done, right? Yeah, but they want you to find the center point here. And this is where it gets a little bit tricky. Like, what are the coordinates of that center point for this osculating circle? Oh my God, you're kidding me. Yeah. Okay. So the way that you can do this is I'm going to walk you through the strategy that I found worked for me, and then hopefully you can follow my line of thinking, and then we'll go do it. So this was my plan. All right. I first am going to look at finding the equation of a tangent line to this point here, 1, 0. And that's just a calculus 1 problem. You've done that in calculus 1 probably a million times, maybe 2 million. Then after we find the equation of that tangent line, y equals mx plus b, whatever, we're going to find the equation of the line that's perpendicular to it. And the reason why is because on this normal line, if you will, a perpendicular line, the center point is, so this is a perpendicular line to the tangent line. That's where the center point is going to lie. And so then once we get that, we can use the distance formula, because we know the distance from this point 1, 0 to this point that lives on the perpendicular line is 2 square root of 2. And so then we'll be able to figure out the unknown, the center point. Because right now we'll just give the center point coordinates of x, y. I have no idea what it is, but we'll figure it out. So that's my plan. First get the tangent line, then come up with the equation of the perpendicular line, and then use the distance formula, the 2D version of distance formula, to help us locate the center point of the osculating circle. So right now we're kind of done with the Calc 3 portion of this problem. We're now doing like Calc 1 with some algebra thrown in, is basically what we're doing. So I know you're probably like, oh man, I thought I didn't have to do any more algebra. I'm sick of it. Yeah. Okay. So step 1, tangent line to the curve at the point 1, 0. And remember, the curve is y equals ln x, right? And we already got y prime, which is 1 over x, because that's going to give us access to the slope. So the slope at the point when x is equal to 1 would be nice to have. That will be y prime evaluated at 1. Ooh, that's pretty easy. That's just going to be 1. And we know we have the point. So if I use the point slope formula for a line, you saw that in an algebra class probably some years ago, y minus y1 is equal to mx minus x1. We have our m, we got our slope. That's nice, it's 1. And then we have the coordinates of our point, 1, 0. So we'll substitute that into our equation. And then we get the equation for the tangent line. Okay, lovely. So how is that helpful? Well, it's going to help us because we've got this tangent line now. Now we can easily find the equation of a line that's perpendicular. So do you guys remember that when lines are perpendicular to each other, their slopes are negative reciprocals of each other? So the step 2 here, the perpendicular line, is going to have a slope of -1 in order for it to be perpendicular. And it also passes through the point 1, 0. So if we use this y minus y1 equals mx minus x1 all over again, because we can, but now the slope is -1 because we're trying to do a perpendicular line, I get y equals, after distributing my negative x plus 1. Okay, fine. So now what? So if you go back to our diagram, we have the equation for this perp line, which is y equals -x plus 1. Fine. So this point that lives on my perpendicular line is going to have a coordinate, what? XY. So it's got XY, but Y has to satisfy the perpendicular line. So we can substitute -x plus 1 essentially. So first, before I do that though, let's go use the distance formula between the point 1, 0 and our center point, XY. Oh, and I'm running out of room, so let's go to the page. And we're getting close. Close to being done. Yay. Okay, so distance formula. So this is next step, step 3. Distance between 1, 0 and the center point, which we're just labeling XY. So you go distance equals, and you learn in algebra, the square root of, and then you take the sum of the squares of the differences of the coordinates, okay? Now this has to equal 2√2, because that was the radius of our osculating circle. And this y is basically lives on our perpendicular line. So what that means is that y can be replaced with -x plus 1. Well, how does that help us? So now we have this distance, which is 2√2, this square root x minus 1 squared plus, and then y minus 0 is just y. So I'll just substitute the -x plus 1, and this whole mess had better equal 2 square root of 2. Yeah, that has to be true. Now here is the cool beans part. This is 1 minus x squared, but I claim that 1 minus x squared is going to give you the exact same value as x minus 1 squared. Doesn't matter which order you take the difference, you square it, they're the same. So what do I mean? Well, if I replace that -x plus 1 squared with something it's equivalent to, so now what? These are like terms. 1 apple plus 1 apple is 2 apples. This is still equal to 2√2. So how does, what do you mean when I add them together? Well, I got 2 of these x minus 1 squareds happening. Okay, fine. And then when I simplify the radical, I can take the product of those factors. And this, I'm going to get absolute value of x minus 1, but let's just say it's x minus 1. X has to be positive. And then if you divide both sides by square root of 2, looks like the square root of 2's cancel. So x minus 1 had better equal 2. Add 1 to both sides. I get the x coordinate of the center point is 3. Yay! So remember, the perpendicular line was y equals -x plus 1. And if you substitute x equals 3 into that equation to get the corresponding y coordinate, you get -2. So the center of the circle has coordinates 3, -2. Wow. And now you can draw the circle perfectly because you have all the information. And if you passed out during that example, I don't blame you. All right, so this coordinates of that center point was, 3, -2. Cool. And that concludes that example. And now we're done with chapter 14. I'm excited because I want to show you how far you've come. And then hopefully this will sort of make a little bit of sense from where we're coming and then where we're headed. So, and then we're done for the day, and I'll let you go early. So here's what Calculus 3 looks like. I didn't do this on day one. Sometimes I do it on day one, but the first part of Calculus 3, you're done. And we had chapter 13. And what did? We did vectors and some fun and play with vectors. And we also did lines, and we also did planes. That's kind of a very simplistic look at chapter 13. Because you're like, well, is that all we're going to be doing on the midterm? Well, and all of the particulars, like you better know everything about vectors, like how to get the magnitude, how to resolve a vector into its components in 2D. You know how to unitize a vector. You know how to determine if vectors are parallel or not. You know how to take dot products, projections, cross products, and what cross product even means, torque, how to find the equation of a plane, how to find the parametric equations of lines. What does it mean when two vectors are orthogonal to each other? All that stuff goes into that module. But you're done, and you're going to get a nice, wonderful exam on that coming up. The very next module, which we're just finished, has to do with vector valued functions. Everything about vector valued functions. The graphs, the domains, limits, taking derivatives, taking integrals, unit tangent vector, unit normal vector, arc length parameter, curvature. And we'll look at a little bit extra right now before you go. I did want to say something about the acceleration vector, and then we'll be done. But this was sort of a short chapter. The key thing that I want you to get, because we also did projectile motion in there too, is that vector valued functions typically are used to represent motion, whether it's in the plane or space. And that's going to come up again later. Next week, we're going to start a big module here. We're going to look at functions of more than one variable. So instead of just y equals f of x, you're going to have like z is equal to f, and this is an example of two variables, x and y. So you're going to have an x comma y there. And then we're going to do partial derivatives and all sorts of fun and play with functions of more than one variable. We're going to do limits again and domains. And in that module, we'll do a lot of derivatives and stuff like that. I don't want to get into it now. That's what the next 2 weeks are. After that, these two modules are sort of together. We're going to do double and triple integrals. And these two modules together are what we refer to as the multivariable calculus portion of this semester. Very important. So if somebody says, hey, do you know multivariable calculus? You're going to go, yep. After you're done with those two modules, we're going to finish our Olympic trial here with the vector calculus portion of the entire semester. And that's that last chapter where it's going to be like you're going for the Olympic gold, because you have to know all the previous 4 modules in order to understand how to do vector calculus. And we do a lot of physics stuff like line integrals with, and we're going to look at what a vector field is, and fun stuff like flux integrals and some very powerful theorems. Okay, so this is the whole path of calculus 3 and where you're headed. So right now you have completed the first 2 modules. Kudos to you. And your midterm has some of it on there, not all of it. So the last little piece I just want to say, and I'm not going to get too much into it, but it is a physics, folks, important thing, is your acceleration vector, no matter what, is always contained in the same plane as big T and big N. And remember, big T and the T and B frame, we saw that last time, would be going around. So whatever the big T and big N vectors are doing at any point in time, you can think of them as being contained in a plane. Those guys, you're guaranteed your acceleration vector will live in the same plane. That's your guarantee. So the reason why it's so cool is you can always write your acceleration vector as a linear combination of big T and big N. Oh, wait a minute, I thought you said linear combination of like ij, I hat, j hat, or I hat, j hat, k hat. You can always do that with any vector. But you can also write a vector as a linear combo of other vectors. And so we saw that before. And the acceleration vector is no different. You can write it as a linear combo of t and n. And the guarantee here is that your acceleration vector always lies in the same plane containing those two vectors, big T and big N. Now, a sub t, this coefficient of big T, is basically the rate of change of speed. There's a few different things that these can be, and if you take a full-blown vector calculus class at UCSD or at one of the state schools, they'll go into this more. Your a sub n is kind of funky, but it's a function of both speed and curvature. So if you're wondering, like, who the heck cares about curvature other than to find out if something's curvy, it does come up into one of these components of acceleration. So a sub t is your tangential component. A sub n is known as your normal component of acceleration. And you're always guaranteed that you can get these. And I go over, some of this stuff. I don't want you to worry too much, but a sub t can also be found by taking a dot product of your acceleration vector with your unit tangent vector. There's another important reason why dot product's important. This is basically a projection. And the normal component can be found by taking the dot product of A with N. There's other formulas to get a sub t and a sub n that are out there. And the most important thing that I want you to know is you may see these in the future. And so it's good to know they're out there. Okay. So that concludes chapter 14. Congratulations.